So let's start the lecture number 6. So here, as we previously see that how one can conclude about the null hypothesis, which is dealt with deals with the standard deviation. Now we will see how to test the variance when the mean is unknown. So let's see it. So means are not known here. Means are not known. So here null hypothesis could be in the three category. One is the one-sided test, that is sigma 1 square equal to sigma 0 square. Okay, sigma 1 square equal to sigma 2 square, and alternative hypothesis is sigma 1 square is not equal to sigma 2 square. This is one-sided test. This is one-sided test 1. Now second is H0 sigma 1 square equal to sigma 2 square, or equivalently sigma 1 square less than equal to sigma 2 square. H1 is sigma 1 square greater than sigma 2 square. This is 2. And number 3 is null hypothesis, sigma 1 square equal to sigma 2 square, and alternative hypothesis is sigma 1 is less than sigma 2, or equivalently you can say sigma 1 greater than equal to sigma 2 square. This is our third set of hypothesis. Now since we don't know the means, we will only use the sample mean. So we know that f is equal to s1 square s2 square. This is more prudent way. Where that higher value s1 square greater than s2. This will follow IF distribution with m minus 1 degrees of freedom, n minus 1 degrees of freedom. When sigma 1 square equal to sigma 2 square. Now a convention is to place maximum of s1 square and s2 square in the numerator. And the minimum in the denominator. And test is reject null hypothesis if f is for number 1 f is greater than f m minus 1 n minus 1 alpha by 2, or if f is less than equal to f of m minus 1 n minus 1 comma 1 minus alpha by 2. And from the property of the f distribution we know this is equal to 1 by f of n minus 1 m minus 1 alpha by 2. This is the case for one-sided test. Now for the this is for 1 problem 1. For 2 this will be reject H0 if H if is greater than equal to f of m minus 1 n minus 1 alpha, and for 3 reject h1 if less than equal to f of m minus 1 n minus 1 1 minus alpha, which is equal to 1 by f of n minus 1 m minus 1 alpha. So we get this from the definition of the f distribution. So that's it. Now okay, so that's it. That's all that we will do for the parametric test. Now we will shift our focus toward the non-parametric test. So you see, so well, now from now onward, this is lecture 6. Now we'll shift our focus from parametric test to non-parametric test. Non-parametric test. Okay, now you see, whatever we did in the previous lectures, we always consider that our underlying distribution of the population is either Gaussian or some known distribution. Now it is not always possible to beforehand know what is the underlying distribution, so we have to start working without taking any assumption about the underlying hypothesis. So we'll do from now onward, we'll see how we can do that with the help of non-parametric test. So let's start. So here it is, there are three kind of inferences. Whatever we did in the previous lectures, that's all are inferences. We inference about some property of the distribution from the observed data. We inference, suppose we inference about the parameters values from the distribution of the data. That is the parametric inference. Now here the non-parametric part, we can also inference about some distribution. So let us fx denote some cumulative distribution function CDF of the random variable of the random variable x representing the random outcomes of an experiment. Now the approach of the parametric inference is to suggest on prior current a family that we on the prior we will assume that f is belongs to some known known probability distribution, known family, that these x coming from a distribution that is known to us. We'll assume some distribution, and then we will test or infer some parameter from the observed x that is available to us. Now it is as I have said, it is not always possible that to know what is the distribution. So we will see here how to deal with these situations. Now another thing here also can be possible, that is called Bayesian estimator, that we will see in the upcoming lectures. So let's do this. Okay. So first of all, so you will see in this lecture we will not use any we will not assume that our data is coming from a normal distribution. We will observe the data, and from the data we will make some distribution, and from that distribution we will analyze various things of that thing, but we will not beforehand assume that our data, that means x1 x2 dot xn coming from any distribution, that we will not assume, here. So let's see with the thing. The empirical distribution, the empirical distribution function. So since we don't know the distribution function and we don't want to make an assumption about the distribution function, so let's see what the empirical distribution look like from the observed data. So suppose by repeating an experiment, n times independently independently under the same conditions. One obtains the realization x1 x2 action of a random sample x1 x2 xn from the distribution function under investigation. So let's see. So let us define investigation definition. Say fx. So let's define the empirical distribution function. So the empirical distribution function, or in the short EDF, so EDF, we will write f n x yn, because we are writing our EDF based on n observation. So equal to 1 by n summation of I equal to 1 to n, and the index function, the xi random variable less than equal to x. And what this index function indicate? So index function indicate this index function if, so let's write what this index function indicate. So if, okay, this means use another color here. So I xi less than equal to x will be 1 if xi less than x, and will be 0 otherwise. So that's it. So that's the empirical function. So you see, you observe a set of data. Suppose you observe, you realized a value xi equal to small xi, and that small xi is less than some predefined value x. Then you will see that you will observe your observation is under your preset value. Then you will this value will become 1, and you will sum the all observation which is lesser than a predefined which is lesser than a preset value x, and that will be the empirical distribution function. So essentially it estimate what it estimate. What does this estimate? essentially it estimates fx, the cumulative distribution function fx, that is the probability, what is the probability that x less than equal to small x by the relative frequency so here we will observe the frequency, that means how many times our observed random variable is less than small x, that is the frequency, that is the probability. So we will here use, actually basically use the frequentist view of the probability or the objective view of the probability. And in the, as I have said that as we go through, we will also introduce what is the subjective things of inference, that is Bayesian inference. So that's it. Now here, if the, so let's see one thing, if the order statistics, so we can define this empirical distribution function in this way, and there is another way to define this empirical function. Let's see that. So if you know the order statistic, so if the order statistics, if the order statistics of the random sample, the random sample is x1 less than x2 less than xn, and its sample realization is x1 less than equal to x2 is equal to xn, then an equivalent definition is that if nx is 0, if x is less than xn, that means if I observe in observation, there is nowhere we observe any observation that is below small x. So that's why the probability of our observed inside our observed value, that observation that is larger than small x is 0, and it will be I by n if I observe ith, if I observe that ith observation x is belongs between the ith observation and I plus 1th observation, then we will see that since it is x remains between the xi and I plus 1, it is strictly lower than I plus 1, then we can see that at least I number of random variable is lower than the x. So then our empirical distribution function will be I by n, and it will be 1. You can guess it and you decide that if xn is less than equal to x, then we will say all the observed random variables are below the x, then it will become 1. So this way you can also also define a empirical distribution function. Now let's see some of its property, and from here and here you see that it is a jump function. So you see it is a jump function with each jump is 1 by n and located at the n order statistics, and it is fn is a discrete and always right continuous distribution function this is one thing. This is another thing which is important to define, that if an x you can define if an x as a cumulative distribution function. So these things are important. This thing is important, that it is a right continuous function. Another thing is and you see if the ties are there, then you will the jump size. So this is another important. If suppose another thing is in case of ties say k different observations have the same value, then the jump size will be g by n. That's all. Another thing is that it is another important thing. Very important thing is if n x tends to closer and closer to fx for all x, if with probability 1 as n becomes large, n that is n is sample size becomes larger and larger. So hence it is a very attractive estimated method of fx. That's it. Now another thing, let's see the property. Means it is estimated. Now let's see whether it is unbiased or not, whether it is unbiased estimated or not. So let's check that. Okay. So properties of properties of empirical distribution function. So let's check whether or not if n is biased or unbiased, or whether it is consistent or not. So to see that, we know that how to see it. So what we'll do, we'll check the unbiasedness of EDF. So we'll see the expectation of f n x is 1 by n summation I equal to 1 to n. Expectation of I xi less than small x and that is nothing but 1 by n. That will be expectation of that I less than x. It is nothing but, this is the probability, this is actually, because expectation, you see expectation of this will be 1 by n into probability of xi, probability of x less than x small x. Since all the you see one thing, you see all xi's are independent, so the expectation of the all xi's will be same, and the expectation of this index function is nothing but the n probability of x less than x, and all, since all are same, so n into p, so this will become probability of x less than small x. And what is this? This is nothing but f of x. So you see that expectation of f and x is actually indeed fx. That means fx is a unbiased estimator. So this means this is in an unbiased estimator. Now let's check it consistent or not. So we'll check it weakly consistent or not. So we'll see the variance of f and x, and the variance means it will become 1 by n square, 1 by, okay, let's see, variance of 1 by n summation of I equal to 1 to n I xi less than small x. So this is so these will came outside n, and this is I equal to 1 to, this is come, this will be n square, this will be variance of xi less than equal to small x I. And you see that the, since xi's are independent, so the variance of all the terms will be same, so this will give you 1 by n square into n this is variance of a index function, that is x less than equal to small x. And the variance of this mean you see what will be the probability that it will occur, that is that probability will be fx, and what is the probability that these things will not occur, that is 1 minus fx. So you can think as this is a kind of a coin toss experiment where the probability of occurring head or getting 1 is fx and getting 0 is 1 minus fx. So what is the variance of that of a one coin toss, that is p into q, that means p into 1 minus p. So we'll get n fx into 1 minus fx, and since these two are finite, so this means as n tends to infinity, these tends to 0 as n tends to infinity. So this is it is weakly consistent. And we can there will be and we can also apply, since we know that its mean is what is the value of this mean, so we can apply the theorem, the central limit theorem, actually T Moivre, the central limit theorem, or you can say T Moivre Laplace theorem. From this theorem it follows that n fn x minus n fx, since n fx is the expectation of these by its variance, so what will be its variance? Its variance is nothing but n into fn x 1 minus fn x. This is a normal 0 1 distribution as n tends to infinity. We'll use this in the various thing. Now let's see the confidence interval of the distribution. So we will use this here to calculate the confidence interval. You see that up to this we have not considered any distribution so far. Now we will use the property of this fnx to write a distribution as if n is very large, then we can say that this follows a normal 0 1 distribution, and from here we will can define the confidence interval for confidence interval of this fnx, that in what confidence level it can estimate the or it can infer the actual distribution fx. So let's see. So this is suppose z is this n fn x minus small n fx root over of n x 1 minus fn x, or you can write it here as fn x minus fx by root over of fx 1 minus fn x by small n. So this will follow normal 0 1. So let's see it pictorially. So this will normal distribution suppose, and here this is, suppose this is fx, this is fnx. Now we want to see that what is the value, and so this is suppose. Now we want to see the what will be the value of fnx, and inside the probability that the remain fx is inside this region is 1 minus 100%, 1 minus alpha. So let me write it, then it will be clear. The probability that these, the probability that these, suppose this is z, I have taken it z, so mod, okay, mod z is less than equal to something, the probability is one minus alpha. So we want to find a value of c for which that these fnx remain in the region such that probability of mod z less than c is 1 minus alpha, which is nothing but that the probability that is probability mod z is greater than c is alpha. So, or we can further you can write that the probability of that minus z is less than minus c is alpha by 2, and probability of z greater than c is alpha by 2. Then the automatically see, then what is the value of c here? So from the standard definition, this is the value of c is minus z alpha by 2. Here z alpha, c is z alpha by 2. So you see that if you write the probability that it remain, so is z is so minus c is, so it will, it means the probability that z will remain inside this region minus z alpha by 2, this is plus z alpha by 2. So the probability of remaining inside is 1 minus alpha, probability is 1 minus alpha, so that means minus c, okay, not minus c, let's put it here what the value is, minus z alpha by 2 is greater than equal to z and less than equal to z alpha by 2, it is the 1 minus alpha percent. That means I estimate such I estimate the fx by fnx, and what my fx will be remain. What is the probability that within 1 minus alpha percentage of confidence that it will remain inside that region? What will be that region? That will I will now calculate. So this means probability minus z, that means that region will be then this minus z alpha by 2 less than z alpha by 2. So this means minus z alpha by 2. Let's put the value of z equal to here. So that is fnx minus fx by root over of fnx 1 minus fnx by n. So first let this side, then we will do that side. So fnx minus fx is less than z alpha by 2. So fx is greater than equal to fnx minus z alpha by 2. So this is that, and from here what you will get fnx minus fx, okay, into root over of this fnx into 1 minus fnx by n. So this is there, fnx is greater than equal to minus z alpha by 2 into root over of this. So fx is less than equal to, this will be, so fnx plus z alpha by 2 into root over of fnx 1 minus fnx by n. So that means that the range will be fnx plus z alpha by 2 into root over of fnx. So you see what is the meaning of this, you can see from here this. So what is the probability that that fx, that our actual probability distribution, actual cumulative distribution will be in this range, will be this range. What is the probability of that? That probability we have just calculated. This is minus of root over of this thing. So you see probability of this will be 1 minus alpha. So confidence level basically means we have to find a boundary, and we will say that within the boundary my actual distribution lies, and the probability of that is 1 minus alpha. So with 1 minus we will give a boundary, and we can say that with probability 1 minus alpha our actual probability distribution or actual cumulative distribution will lie in that region. So that is called the confidence level, a confidence interval. So this is my confidence interval. So the confidence interval is fx. So I think I write it wrongly, this is less and this will be positive, fnx plus minus, so it is minus plus z alpha by 2 into root over of fnx 1 minus fnx by n. So that is our 1 minus alpha percentage confidence interval. So that's all. hmm. Now we'll see another thing. We'll see another thing. The another so we'll see another thing that is very important to know, which is called bootstrap method. Okay. Okay. Now non-parametric bootstrap. Non-para. Now we'll see this. So what does it mean? It means, so we will not assume anything else, and using the distribution on my hand, using the data in my hand, I will find the most of the things that I require. So that is called bootstrap. So whatever I have in my hand, I will use that to find the everything else. So let's find it. So first we need the, don't need, but I want to write the how you can calculate the mean of the distribution, that is mu cap is minus infinity to plus infinity x fn x dx. So you see, okay, so I haven't write it correctly, so here I have to write it probability. What is the differentiate of this thing? So this is 1 by n summation of I equal to 1 to n xi. So that is the mean, actually that is the sample means, and it is sample mean and its variance, thus its variance or sample variance sigma square equal to minus into plus infinity x square d of f and x. So that will be 1 by n summation of I equal to 1 to n xi square. Okay, so to variance means I have to delete another thing here. Okay, is mu with square. So you see this will be 1 by n summation of I equal to 1 to n xi square minus x bar x square or mu square. So that is variance. So you see as n tends to infinity, its mean goes to the mean and variance goes to variance. So these will the consistent you will see consistent estimated, but you see that sigma square is not a unbiased estimated. So that's it. Now another thing, whatever we want to discuss here, that is let w is equal to is a function of x1 x2 xn. So as we have write the sample mean, so sample mean variance, which is a function of these random variables. Here suppose that w is similar to kind of random variable, which is also a function of this random variable. This is a this BA statistic based on the random sample x1 x2 xn. Then the EDF or then the CDF of GW small w means this the CDF can be estimated by say m n observation, m this type of observation x1 x2 xn. If we know since this is a function of w and w contains the x1 x2 xn, so different set of x1 x2 xn will give the different set of value of w. So to generate a CDF or to estimate a CDF, we need suppose m numbers of this type of distinct observation, x1 suppose x1 prime, x2 prime, xn prime. So this type of n set of m suppose m set of these numbers. Now how the question is, how can you generate this m distinct set of n vectors, n random variable vectors? So one way is you can generate these n random variables by from the actual distribution, distribution fx, or you can do the experiment, do the n times experiment m times. That means if you do m into n times total experiment, you will get such a set of m vectors, and from that you can estimate the GW. But now what we will do, we here in the bootstrap method we don't want to use the actual distribution fx to generate this random variable. What we will do, we will use our EDF, that is fx, will use this to generate at m such observations. So you see, we only have these n observation, and from that observation we make a distribution fnx, and from this distribution we will again generate m such kinds of random vector, m vector. That means we are bootstrapping whatever we have in our hand. To use that, we will again generate m vector, and from there we will estimate the GW. So how we will, now question arises, how we will generate that? How does one generate m such vectors? Now here it is interesting to how we will generate. So now obtaining observations from fnx essentially means essentially means sampling an observation sampling n observations from the original sample x1, x2, xn with replacement. So you see, since we have this set of vectors, now what we will do, we will generate another set of random vector by randomly choosing these numbers from a number from these sets, and will replace that number. That way we will again generate another random vector with n entries, and that will be different from this, and again we will do the same method m times, and we will generate m such random variable. So you see here, suppose from here I will see 1 2 3 how he will generate. So he will generate, suppose 1 is 1 1 2, 1 is 2 3 1, 1 is 2 3 3. So that way from this original sample you generate randomly 3 different random set of vectors. So that way you will generate m observation. This is called bootstrapping. So from your observation you will get this m different kind of observation, and from this m different kind of observation, now following the same methods you can calculate the this is called bootstrapping sampling, and now you can get a m different types of, this is called bootstrapping sampling. Now what are the bootstrapping sampling? One is w1 star, so this is, you will get w's 2 stars. Now if you put these values into this function w, this function, you will get another m set of thing. So you will get, suppose, m set of such vectors, and from this m set of vectors you can easily calculate, suppose one of that function, you can calculate these wm summation of wi star, and you can also find sigma square using 1 by m summation of I equal to 1 to b wi star square minus mu, sorry, this b, so bootstrapping mu b w square. So that's why you will get, and as we have done previously, so you can also estimate the distribution of these CDF, so that also you can do. And how many sample you can collect from here, that will be equally likely. So let's write how many sample you can collect. So this is very interesting indeed. So suppose there are n numbers are there, suppose there are n numbers x1 x2, n numbers are there, and if you put 0 1 2 dot 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 n minus 1, and if you choose and generate another number, suppose you will choose k number from here, suppose you will choose this, and suppose you will choose k number, you will see that summation of that will be, okay, let me see. So how will get the thing, that is very interesting. So if you do like this, okay, how many sample you collect, that will be the number of, so I am asking the number of distinct random samples of size n from the values x1, x2, xn through sampling with replacement. And what will be that number? That number is actually 2n minus 1 cn, and we will see in the next lecture how one actually get this value, and we will finish this bootstrapping method, and we will do 1 and 2 exercise in this regard, and we will finish this empirical distribution function. So thank you.